So as I mentioned, we'll go one by one through the numericals. I'll give you some time to attempt it and then we'll look at the solution. The first example is, or the problem is, of a steam power plant. It receives heat from a furnace at a rate of 280 gigajoules per hour. Heat losses to the surrounding air from the steam as it passes through the pipes and other components are estimated to be 8 gigajoules per hour. Furthermore, it says that if the waste heat is transferred to the cooling water at a rate of 145 gigajoules per hour, you have to determine the net power output and the thermal efficiency of this power plant. So have about 2 to 3 minutes to attempt this problem and then we'll try to figure out how to solve this. All right, I'll give you 2 to 3 minutes to solve this problem, and to whatever extent you can do, just try to attempt it so that at least you get a first chance to attempt, and then we'll look at the solution. All right. In the meanwhile, while you're attempting, let me draw the steam power plant for you so that it becomes a little easier for you. I've drawn the schematic for you so that the statement becomes a little clearer to you. Has anybody solved the problem as yet?
Yes, sir.
Very good. So what's your answer? I'll just write down the answer over here for part A. I'll just write it down.
127
120
gigajoules per hour. And
gigajoules.
efficiency is 45%.
All right, so I'll just write down the answers. I'll not confirm whether it is correct or not until we go through the solution. Who is this, by the way?
Daniel.
Dania, very good. Anybody else who have got some different answers? Is there anyone else who has attempted it and got some different answers? No? All right, let's look at the solution first. So always remember the steam power plant, it consists of four components: pump, boiler, turbine, and condenser. It's an external combustion engine where you're receiving heat from the furnace which is outside your system. Your system essentially composes of four. This heat engine basically composes of steam power plant is composed of four components which are within the dotted. So I had to switch to some other connection anyways. So this is your heat engine. I hope it is visible to you. Again, four components, and these four components, they are connected by the pipelines that I am highlighting with uh, blue color. So these are the connecting pipelines, and it says, if you look at the statement, it says that the furnace is giving in the heat at a rate of 280 gigajoules per hour. So the heat that is coming to the system is at a rate of 280 gigajoules per hour. Before we move on to see the losses, we see that the waste heat is transferred to the cooling water at 145 gigajoules per hour. So Q dot L, which is being moving out of the system, is essentially 145 gigajoules per hour. Now you are familiar with both the two heat transfers. It further says that 8 gigajoules per hour is being lost to the surroundings through the pipes and other components. So these three other components: pump, turbine, and condenser, they are also, along with the pipes, they are losing heat losses They are at the rate of 8 gigajoules per hour. Now, if you remember the net power output, work net out is essentially what is coming in the form of Q dot H. This is coming into the system minus what is being moving out of the system. So there is Q dot L which is moving out of the system. Other than this, Q losses are also being rejected or are moving out of the system. So Q dot losses would also be uh, wasted as a result of the losses from the pipes and other components. It's simple enough. You just have to plug in the values 280 minus 145 minus 8, and this would essentially give you 127 gigajoules per hour. Is it so?
Yes, sir.
All right. So this becomes your net power output. The second part is you have to determine the thermal efficiency of this power plant. If you remember the formula for thermal efficiency of a power plant, it is nothing but the net power output, work net out, divided by Q dot H, what is coming into the system. So essentially what is coming into the system is 280 gigajoules per hour is the energy which is coming into the system, and out of this energy which is coming into the system, the work generated or the net work output is essentially 127 gigajoules per hour. I think this becomes equivalent to 0.453, I guess.
Yes,
Yes,
sir.
sir.
4535.
All right, so this is essentially equal to 45.3%. So the efficiency of your power plant is 45.3%. If you compare it with the efficiencies, the range of efficiencies mentioned for power plant, the efficiency of a power plant is, I guess, mentioned in your slides is about 60% at max. So it's in the range for a steam power plant. Clear enough? Is the solution clear?
Yes, sir.
All right. So the solution has already been done for you. I'll erase the one that I've done right now. So this is the solution. You could also refer back to it once you are revising. The second problem is that an automobile engine, it consumes fuel at a rate of 28 liters per hour and delivers 60 kilowatt of power to the wheels. If the fuel has a heating value of 44,000 kilojoules per kg and a density of 0.8 grams per centimeter cube, you have to determine the efficiency of this engine. I'll give you 2 minutes, but before that, I'll give you a hint. 0.8 grams per centimeter cube is essentially same as 0.8 kgs per liter. 0.1000 grams is equivalent to 1 kg and 1000 centimeter cube is equivalent to 1 liter. So grams per centimeter cube is essentially same thing as kgs per liter. Considering this, you have to find out the efficiency of the system. If you want, I can draw the schematic for you also. So you have this automobile engine. This is receiving heat. Uh, you could say Q dot H, delivering some power, which is W dot net out, and rejecting some heat, Q dot L. So you have to determine the efficiency. The formula for efficiency, I'll write it for you over here. We have already discussed it. Is essentially net work out divided by Q dot H. Now you are basically interested in, as far as the question is concerned, you are basically interested in this portion of your heat engine. I'll leave it to you to solve it. I'll give you 2 minutes. Kindly solve it and then we'll look at the solution. With the help of the schematic that I have drawn, try to solve it and then we'll look at the solution. All right, 2 minutes. If someone has solved it or is about to solve it, kindly let me know so that we could continue. In the meanwhile, I'll wait for 1 more minute.
Sir, 22%? Yes, sir. Yes, 21.9%.
All right, it's good to see that people are getting the answers. 21.9%. Let's see if the answer is correct or not. All right, so those who have solved, what is the net power output?
As a 60 kilowatt.
All right, so the net power output, as it says, delivers 60 kilowatt of power to the wheel is 60 kilowatt. So when I look at this expression, I know that work net out is known to me. Work net out is work net out. The rate of work delivered by the engine is known to me. I have to find out the value of Q dot H, and the information regarding Q dot H, what is given to me, this Q dot H is essentially coming from the burning of the fuel, and the rate at which the fuel is being consumed is given to me as 28 liters per hour. Density is also given to me. This rate, which is 28 liter per hour, it is essentially the volume flow rate, and density is represented by rho. So if I want to find out the mass flow rate, the mass flow rate is essentially equal to density multiplied by the volume flow rate. Density I know is 0.8 liters, sorry, kgs per liter, which is multiplied by the volume flow rate, which is 28 liters per hour. This would essentially become, the liters would cancel out. What is 0.8 times 28?
Sir, 22.4.
So this is 22.4 kilograms per hour. Now, if I want the heating value of the fluid or fuel is also given to me. The heating value of the fuel, which is energy per unit mass, is given to me. So if I want to calculate the energy associated or released due to this heating fuel, which is essentially Q dot H coming from the fuel, it is essentially mass flow rate multiplied by Q of the fuel, or small q of the fuel, which is energy per unit mass. Mass flow rate is known to me as 22.4 kg per hour multiplied by the energy of the heating fuel, heating value of the fuel, which is 44,000 kilojoules per kg. Essentially kg would cancel out and you will have what is the answer? 22.4 multiplied by 44,000.
Sir, 985600 kilojoule per hour.
985,600 kilojoules per hour. Now, if you look at the power or work net out, it is given in kilowatt, which is essentially kilojoules per second. So I need to be consistent with the units. I'll convert this heat energy rate in terms of kilojoules per second. In order to do that, I'll have to divide 985,600 kilojoules with 3600 seconds. This would give me what?
273.78.
270
3.78.
273.78 kilojoules per second or kilowatts. Now I can plug in the Q dot H value to find out the efficiency, which is work net out divided by Q dot H. Work net out is 60 kilowatt and The Q dot H is essentially 273.78 kilowatt. This would give me what?
21.9%.
All right, so this would give me 0.219, which is essentially equal to 21.9%. All right, clear?
Sir, kindly the last step.
Sorry,
Sir, kindly the last step.
the last step. Sorry, which one? Can you identify the step that you're referring to?
The efficiency, sir.
The efficiency. How do we determine the efficiency?
Yes, sir.
So, what is the formula for efficiency for a heat engine? Jitaha, what is the formula for efficiency of a heat engine? Work dot net work out of the heat engine divided by the heat provided to the engine. If you are expressing both of them in the rate form, work net out divided by Q dot H. Clear?
Yes, sir.
What is work net out?
To work it out is 60 kilowatt.
So I'll write 60 kilowatt over here. And what is the rate at which heat is supplied to the system? Q dot H.
273.78.
273.78, both in kilowatts. Kilowatts would cancel out. This ratio would be 0.219. So if you multiply by 100%, this would be 21.9%. Clear?
Yes, sir.
All right. Now let us have a look at another problem. The solution is already there for you. You can go through the slides. It says that a coal burning steam power plant produces, again, coal burning, external burning steam power plant produces net power of 300 megawatts with an overall efficiency of 32%. 32%. The actual gravimetric air-fuel ratio in the furnace is calculated to be 12 kg of air to 1 kg of fuel. The heating value of the coal is 28,000 kilojoules per kg. You have to determine the amount of coal consumed during 24-hour period and the rate of air flowing through the furnace. I'll quickly draw the schematic for you so that you have an understanding of what is happening. This is again a steam power plant. You have pump, a boiler, then you have a turbine, and then you have a condenser. Now this is your steam power plant. All right, so you have a coal burning, you have a furnace over here which is giving you a heat, coal fired furnace. So essentially you have air and fuel coming into the furnace. As a result of this burning, you get Q dot H into the system, and Q dot L is released to the surrounding. The net power W dot net out of this engine is 300 megawatts and the efficiency is 32%. Now the information also given to you is that for 12 kg of air you are using 1 kg of fuel. Fuel is the same thing as coal. What? So the essential thing is you are interested in, you have been give you are interested in this portion, amount of coal consumed and the air, the rate of flow of air. So essentially you are interested in this region of your diagram. Now if you are interested in this region, you have to move towards this region. So what is the first thing that I should find out?
Q dot H.
Very good. So
Heat supplied to the
sorry. Now efficiency, it is given to me. The net work out is given to me. This would help us find Q dot H. So if I just want to find out Q dot H, it is essentially work dot net out divided by the efficiency, which is 300 megawatts is the work net out divided by 0.32, which is the efficiency. So what is Q dot H?
So 96 megawatt.
Are you sure?
937.
No, sir,
937.
937 actually, sir.
Sorry?
937.5.
So you have 937 megawatts of Q dot H, or I could also write it as 937 megajoules per second. This is Q dot H that is coming to me. Now, if I want to find out the amount of coal consumed within the 24-hour period, can I find out the energy consumed in 24 hours period? Can I find out Q dot for 24 hours? Or sorry, not Q dot, it is
QH.
yes. Can I find
Yes,
out
sir.
QH for 24 hours?
Sir, multiply by 3600 multiply by 24.
Very good. So you have 937 megajoules per second. If you have to find out the energy for 24 hours, you'll have to multiply by 24 hours into 3600 seconds. And this would give you the energy consumed in 24 hours. So what would be this energy?
8.1 into 10 power 7.
8.1 into 10 power 7 joules. Is it so?
Sir, megajoules.
Megajoules.
Yes.
All right. This is the energy consumed. Now, this energy is coming from coal, which has a heating value of 28,000 kilojoules per kg. That means the fuel that we have, it gives 28,000 kilojoules of energy for 1 kg. If I am consuming this much amount of energy for 24 hours, how many coal would have been consumed?
We will divide them.
Divided by 28,000.
Very good. So the mass of coal consumed or fuel would essentially be what? It would be 8.1 into 10 is to power 7 megajoules divided by 28 megajoules per kg. I have converted 28,000 kilojoules into 28 megajoules per kg. This would give me how much amount of coal?
2.89 into 10 to the power 6 kg.
2.89 into 10 is to power 6 kgs. First part is done.
Yes, sir.
The amount of coal consumed during 24-hour period. Now, if I want to find out the rate at which this coal was fed for 24 hours, the mass flow rate of coal or fuel, how can you find it out? The units are kg per second.
So
Sir,
divided by time.
It is the mass, which is 2.89 into 10 to the power 6 kgs, and it is consumed
Multiplied by
in
12.
24 into 3600 seconds. This would give me the rate at which this coal was fed. Clear?
33.5.
Sorry?
Yes, sir.
33.5.
33.5 kgs per second. This is the mass flow rate of fuel or your coal. Clear? So far, is it clear?
Yes, sir.
Now you have
सर
been
एक्सक्यूज
given
मी सर
G.
ये बता दें कि ये डिवाइड क्यों किया हमने ये जो 8.1 क्रॉस 10 प्लस 7 डिवाइडेड बाय 28 मेगा जूल
It is, if I want to find out that at what rate the coal was being provided to the furnace, I know that this much amount was used in 24 hours. This much amount in 24 hours, the rate would be at 1 second, 33.5 kg was being transferred to the furnace. Clear enough?
सर ये ऊपर वाला भी बता दें ये जो डिवाइडेड बाय 28 हमने मेगा जूल किया था ऊपर जिससे 2.89 आंसर है
You know that the amount of coal or the energy that was provided to the furnace is 8.1 into 10 to the power 7. This is the energy, and for each kg, 1 kg of coal gives you 28,000 kilojoules energy or 28 megajoules energy. So how much coal was required to give you 8.1 into 10 to the power 7 megajoules of energy? It is this much amount of coal, 2.89 into 10 to the power 6. Clear?
ओके सर क्लियर थैंक यू
All right, you're welcome. So the mass of air to mass of fuel is essentially 12 over 1. Clear? Is this clear to you?
Yes, sir.
This means that mass flow of air would also be 12 is to 1 if you divide both of them per second. Clear enough?
Yes, sir.
So if I want to find out the mass flow of air, it is essentially the 12 times mass flow rate of fuel or coal. So can you find out the mass flow rate of air?
401.
Sir, 401.78.
So this is 401.7 kgs per second. Is this point clear to you?
Yes, sir.
Yes, sir.
All right. Great. So now we'll look on. The solution is already there. I'll erase this one. So you have the solution for you. You can always go back and have a look at the solution. Another problem that we have is that a heat pump is used to heat a house that has a coefficient of performance of 2.5. This is being claimed. It is said that the heat pump delivers 2.5 kilowatt of energy to the house for 1 kilowatt of electricity it consumes. I'll show you a heat pump. If you have a heat pump over here, it is delivering 2.5 kilowatt of energy, which is QH, for each work in, which is each kilowatt of energy. For 1 kilowatt of energy, it is giving me 2.5 kilowatt of heat. I have to see whether is this a violation of the first law of thermodynamics, and I have to explain that. Now, if I see this as my system, heat pump as my system, I know heat pump takes in QL from low temperature reservoir and delivers it to a high temperature reservoir. while there is some work being done into the system. If I have to apply energy balance on a heat pump, how can I apply the energy balance on a heat pump? Whatever is coming in is essentially going out. E in equals to E out. E in is work in, again coming to the system, plus QL, again coming to the system, essentially equal to QH moving out of the system. All right. I know QH is 2.5 kilowatt hour. Work in is 1 kilowatt hour. What should be the value of QL that would satisfy this equation?
1.5 kilowatt hour.
So if my QL is 1.5 kilowatt hour, that means it satisfies the first law. Clear enough?
Yes, sir.
Yes, sir.
Now, I have been given COP as 2.5. COP is basically for a heat pump QH divided by work net in. All right.
Yes, sir.
And work net in, if you say, is QH over QH minus QL. So if COP is given to me as 2.5 and the QH is essentially 2.5. Sorry, COP is given to be 2.5 and QH is also 2.5 minus QL. Can I find out QL from this equation?
Yes, sir.
What does it comes out to be?
1.5.
So that means
1.5.
that for this system, the first law is satisfied. Clear enough?
Yes, sir.
Is it?
Yes, sir.
All right. So in this case, we'll say the question is this a violation of the first law of thermodynamics? We'll say no, since no energy is created or destroyed, the heat pump satisfies first law. Clear enough?
Yes, sir.
All right. So we'll stop over here. We'll have few more numericals to see that will be, sorry. We'll be looking at in our class tomorrow. Is Hamza here?